electric motors and electromagnetic induction. First of all, we will read overlapping magnetic fields. Look at this setup. Current is flowing through the wire when the switch is on. There is a cell connected. When current flows through the wire, there is a magnetic field around the wire. This magnetic field and the magnetic field of the permanent magnet interacts, and due to interaction there is a force onto the wire and the wire moves. I repeat once again. Look at this setup. This is a permanent magnet, north to south pole. You can see the magnetic field lines. These are blue marked lines, north to south. There is a wire, there is a switch, there is a cell. So when the switch is closed, electricity from the cell, it passes through the wire, and when electricity goes through a wire, it produces a magnetic field around it. That magnetic field we cannot see here, but that magnetic field and the magnetic field of the permanent magnet interacts. Due to this interaction, there is a force onto the wire and the wire moves. Now, what would be the direction of movement? Left hand rule says this. Left hand rule. First finger shows you set up your left hand this way. Look at this arrangement. First finger shows the direction of north to south, the magnetic field of the permanent magnet. Then second finger shows the direction of current through the wire, and you just hold your hand this way, like this arrangement of three fingers. That first finger shows the direction of north to south, second finger shows the direction of current through the wire, then thumb indicates the direction of force onto the wire. Thumb indicates the direction of force onto the wire. So now in our arrangement, the arrangement that we have, look at this. Now this is the direction of second finger and this is the direction of first finger, and thumb indicates the direction of force onto the wire. So this is called Fleming's left hand rule. It's very important. It's called Fleming's left hand rule. It's very important. And there is an application of Fleming's left hand rule. Look at it. Look at this. This is a loudspeaker. An application of Fleming's left hand rule. Look at the permanent magnet, north south and north south. Look at the blue magnetic field lines. And signal from the source means that signal is coming, loudspeaker, that is the flow of current into the wire, and that wire there is a magnetic field around it, and that magnetic field and the magnetic field of the permanent magnet, they overlap, they interact, and there is a force produced onto the wire, and this wire cannot come out because this wire is fixed into the case in different places, and it just vibrates. As the wire vibrates, the paper cone vibrates, and the paper cone vibrates, the sound signal is coming out. Look at this, the sound signal is coming out as the paper cone is vibrating. So again, once again, I repeat, this is an application of overlapping magnetic fields, or Fleming's left hand rule, that what actually we have seen right now. When this is permanent magnet, you can see the permanent magnet, you can see the magnetic field lines from north to south of the permanent magnet. Signal from the source is coming, that is the electricity is coming into the wire. When the electricity flows through the wire, magnetic field produced around the wire, that magnetic field and the magnetic field of the permanent magnet, they interact each other, and due to this interaction there is a force onto the wire and the wire moves. And according to the left hand rule, you must always follow in this situation the left hand rule. The left hand rule says that first finger indicates the direction from north to south. Second finger indicates the direction of the current flows through the wire. Then, according to your arrangement, thumb indicates the direction of force. So, as the direction of force, the movement of the force of the wire moves, and here the wire cannot come out because it is fixed into the case, and the wire just vibrates. And as the wire vibrates, the paper cone vibrates, and sound signal is coming out. Sound wave is coming out. Look at the sound wave. Look at the sound wave. It is coming out. This is electric motor, another application. Look at the arrangement. These are permanent magnets, north, south, north pole, south pole of permanent magnet. Look at the wire, the combination. Look at the blue lines, north to south. Look at the supply voltage. When there is a supply from here, look at this. Electricity going this direction. I repeat, when there is a supply, electricity from here, it is going this direction. So this is the path of the electricity that I drawn. And there is a north to south. If we place first finger, and in every place, if you consider this side, and if you place first finger north to south, and the direction of current would be in that direction, into the direction of the textbook. That is a direction of second finger. Then thumb indicates the direction of the movement of the wire, and that is downward. Thumb indicates the direction of the movement of the wire, that is downward. And if you place your left hand in this side, if you place your left hand in this direction, then what would happen? That current is coming towards you, as the electricity is coming towards you, and not to south pole, that is first finger, and electricity direction through the wire, it is second finger. So thumb indicates the direction of the wire, movement of the wire. So look at this, one is downward arrow, one is upward arrow. So this side moves downward and this side moves upward, and it continues and this rotates. This loop of wire, or it is called also shaft, this shaft, it rotates. As it rotates, this is the concept of electric motor. This is the concept of electric motor, that it rotates. And how can we increase the speed of the motor? We can increase the speed of the motor by three ways. We can increase the current flow, we can increase the number of loops into the wire, and we can increase the magnetic field stronger. We can increase the strength of the magnetic field. We can increase the strength of the magnetic field, or we can use stronger magnet. These are the three ways. Once again, I repeat. How can we increase the rotation of the motor or speed of the motor? By three ways. We can do it by three ways. By increasing the current through the loop of wire, by increasing the number of loops into the wire, and by increasing the strength of the magnetic field. So this is about electric current. And look at this. This is split ring commutator and this carbon brush. These all actually, split ring commutator helps to rotate the shaft inside of it. And the carbon brushes, look at the carbon brushes, it helps as connector. It helps as connector. Now we will read electromagnetic induction. What is electromagnetic induction? Electromagnetic induction is that, look at this setup. This is a permanent magnet. There are blue lines north to south, and there is a simple wire. And a part of the wire is between the north and south poles, or it is through the magnetic fields of the permanent magnet. Now, if we move the wire, if somehow we move the wire cuts the magnetic field lines. I repeat, if we move the wire up and down, for example, the wire cuts the magnetic field lines. So voltage induced into the wire and electricity flows through it. This is called electromagnetic induction. I repeat once again. And if you connect an ammeter in series into the wire, you see the reading into the ammeter that there is a net flow of electricity. So I repeat, if we place a wire into a magnetic field, and if the wire is moving, it cuts the magnetic field lines into the magnetic field, then voltage induced into the wire and current flows through it. This is called electromagnetic induction. And as the current is flowing through the wire, we can measure it by using an ammeter. If an ammeter is placed onto the wire, the ammeter would give a reading, or if it is an analog ammeter, it would deflect to show that there is a net flow of current through the wire. This is electromagnetic induction. So what we need to do, somehow we have to move the wire so that it can cut the magnetic field lines. Now, opposite is also true. We can fix the wire in a fixed position, and we can move the magnetic field so that it cut the wire. Same thing. Now, if the wire is fixed, and if we move the magnet in a way that the magnetic field lines cut the wire, there would be also voltage induced into the wire and current flows. It would happen that voltage would be induced into the wire and current would flow. This is also electromagnetic induction. Somehow the magnetic field lines cut the wire, or what the wire cuts the magnetic field lines. It should happen. This is the concept of electromagnetic induction. Now we will see the second part that I said. Look at this. This is a moving magnet into a coil. Now here, the coil of wire, it is fixed. And look at the ammeter connected in series. Ammeter connected in series to measure that is there any current is flowing through the wire or not. To measure the current, ammeter is connected in series with the wire. So when we insert the bar magnet into the coil, as you see the diagram, if we insert this bar magnet into the coil, as you see the diagram, what would happen? Look at the magnetic field around the bar magnet. Look at the magnetic field around the bar magnet. The magnetic field would cut the coil, and there would be voltage induced into the coil and current would flow. This current can be measured by this ammeter, and this is called also induced current. And this total scenario is called electromagnetic induction. And how can we increase the size of the voltage or size of the current? By moving the magnet quicker, by using stronger magnet, and using a coil with more number of turns. Look at these 3 points. These are the 3 ways that we can increase the induced voltage or the flow of current through the wire. There are 3 ways: by moving the magnet quicker, using a stronger magnet, or increasing the strength of the magnetic field, or we can increase number of turns into the coil. And this is the concept of generator. This is the concept of generator. Look at this. This is the concept of generator, and it is also called alternator because it produces alternating current. Look at the concept. There is magnetic field. This is a magnet, and this is the north pole. This is a magnet, and this is the south pole. This magnet is actually like this way long. This is a part. This is the north pole part, and this is the south pole part. And this magnet is also like this way. It's a big magnet. In this direction, there is north pole. This is the coil. When we move the coil, somehow we have to rotate the coil. The coil rotates and it cuts the magnetic field lines. Then voltage induced into the coil and current flows, and that current and voltage is collected from here. Look at this. The induced AC voltage is here. We'll get the connect. There are two terminals from here, and now if you connect a bulb here, the bulb will light on. And this is AC supply. This is the general concept of producing AC supply. So somehow we have to rotate the coil. The coil in power station that rotates into the magnet, it is called actually generator. Rotating coil inside magnet is called actually generator. I repeat, rotating coil inside magnet is actually called generator. And when it rotates, it cuts the magnetic field line, voltage induced, and current flows, and electricity produces. It generates electricity. That's why it's called generator. So this is the concept of electromagnetic induction. Now, after producing this electricity from the power station, what happens? This power station electricity is then transmitted to long distances by using transmission cable. So before transmission cable, a transformer is used, which is called a step-up transformer. And after transmission cable, another transformer is used, which is called step-down transformer. So now we will read the concept of transformer. Look at this. This is the transformer, basic structure of a transformer. The soft iron core. There's a primary side and the secondary side. In primary side, coil of wires are wound around it, and in secondary side, coil of wires are wound around it. And this side is called primary coil. The coil in this side is called primary coil, and the coil in this side is called secondary coil. So when look at this, the number of turns of coil is much greater than the number of turns present here in secondary coil. Primary coil has more number of turns. That's why the voltage produced here will be lower, and it is called step down transformer. And if it has more number of turns, secondary coil, then the voltage produced here would be bigger or larger, that it would be called step up transformer. So in the diagram that we see, it is step down transformer. Look at this. More number of turns in primary coil and less number of turns in secondary coil. This is iron core. Electricity is coming to the primary part, and there is a magnetic field developed around it, and this magnetic field cuts the secondary coil. Look at the magnetic field. This magnetic field cut the secondary coil, and electricity or voltage induced into the secondary coil, and this current is going like this through from here. So this is the diagram of a step down transformer. I can write it here for you. There is a relation between the number of turns in primary NP and the secondary number of turns of coil NS, and input voltage VP and output voltage VPS. VP by GS equals to NP divided by NS. Number of input voltage in primary divided by output voltage in secondary equals to number of turns in primary divided by number of turns of coil in secondary. Vp by Vs equals to Np divided by Ns. And this is a step down transformer. What happens? Due to small number of turns in secondary, the voltage obtained in this case, Vs, secondary voltage, is smaller. A secondary voltage, in both case, input power equals to output power. Input power equals to this output power. And power equals to, power means I multiply V equals to I multiply V. Now, as I'm saying that in this case, as it is a step down transformer, secondary voltage decreased. So Vs would be smaller than Vp. Then what would happen to keep the equation fine, input power equals to output power? Generally, we can understand that current would be greater in secondary than the current in primary, so that both multiplication, this IV and this IV, becomes equal, or it stays equal. So this I is actually IP multiply Vp equals to Is multiply Vs. So what I'm saying, to keep this equation fine, as it is step down transformer, this Vs is smaller. Vs is smaller than Vp, and to satisfy the equation, Ip is smaller than Is. Secondary transformer, Vs is smaller, but Is is greater. Voltage is smaller than the primary voltage, and current in secondary is greater than the primary current. Is for secondary current, Ip for primary current, Vs for secondary voltage, Vp for primary voltage. So this is step down transformer. And what happens in step up transformer? In step up transformer, secondary has more number of turns. Secondary coil has more number of turns. What I can write it for you. This is not written here. Look at this equation is written here. Input voltage divided by output voltage, number of turns in primary coil divided by Np by Ns. So please mark it. This is a very important equation, and keep it in a block diagram. And here there is a simple math regarding this equation. And the primary transformer has a primary turns 100 turns, and secondary turns is 500 turns. So Np, this is Np, and this is Ns. And alternating voltage, 2 volt is applied to the primary, means Vp. Vp is 2 volts. On the secondary, look at this. This number is high number, greater number. Ns is greater, so it is step up transformer. It means the secondary voltage will be greater than primary voltage. Now, putting this equation, look at this. Secondary voltage, definitely it came larger or greater than primary voltage. So this is step up transformer. This math is the example of step up transformer, and the example previously we have seen, there is example of step down transformer. So I was talking about this is step down transformer. Let me write it. Step down transformer. And what would happen if these things change for step up transformer? And step down transformer, look at this, secondary has less number of turns of coil than primary. This is step up down transformer. And now for step up transformer Vp, just it will be reverse, would be Vs. Step up transformer, Vs would be greater, and Ip would be Is, and secondary has more number of turns than the primary coil. This is step up transformer and step down transformer basic concept. Please keep this note reserved. It would be helpful for you in future. This is the basic part of the transformer. And you have to remember that input power remains equals to output power. Now look at this step up transformer, where it is used. If the step up transformer used after the power station before the transmission cable. It is used after the power station, sorry, and before the transmission line. And step down transformer is used. It is used uh, after the transmission line, before it before the electricity reaches the home, before home. Step down transformer. So in our home, it is low voltage, we get 230 volts around, and transmission line, it has high voltage and less current. Due to less current, less energy wasted. Due to less current in transmission line, less transmission line is less heated and less energy wasted, and it can be carried to long distance. So this is very important note, what actually I wrote here. So this is all about transformer from our syllabus.